welcome to a new episode of Know Your Scientist series brought to you by Kshama Ahmedabad Academy of Sciences. Today we are delighted to host Dr. Vishal Vasan, a mathematician whose work lies at the fascinating intersection of pure mathematics, applied problems, and computational science. Dr. Vasan is the Reader F at International Center for Theoretical Sciences, ICTS TIFR, Bangalore. He has completed his bachelor's degree in mechanical engineering from Anna University in 2005, followed by a master's degree in mechanical engineering from Arizona State University in 2007. His passion for mathematical theory led him to pursue a PhD in applied mathematics from the University of Washington in 2012. He went on to hold the prestigious S. Chawla Research Assistant Professorship at Penn State University before joining ICTS in 2015. Dr. Vasan's research primarily explores the theoretical and numerical analysis of partial differential equations with applications in inverse problems, fluid dynamics, and dynamical systems. He is also deeply interested in the convergence of mathematics and data science, a rapidly growing area of interdisciplinary research. A dedicated teacher and a mentor, Dr. Vasan has guided PhD students and postdocs and has taught a range of advanced courses in mathematics. He has been recognized as an associate of the Indian Academy of Sciences 2020 to 2023 and is a member of National Academy of Sciences, India since 2018. It's a pleasure to have you with us today, Dr. Vasan. Thank you for joining.
Thank you.
You began with a degree in mechanical engineering.
That's correct.
Then transitioned to applied mathematics.
Correct.
What sparked this change in direction?
I wouldn't say it was actually a change in direction. I think, like a lot of people in India, I followed a traditional path of doing engineering without much thought, and then perhaps either just before or during, I sort of realized I wanted to do something else, and I think the journey I took was more the long road back to what I was interested in, as opposed to having a sudden change.
Usually in India, when the conventional path, as we talk about engineering, people do about bachelor's in engineering and then they
Correct.
start tutoring.
Correct.
Choosing masters in
That's right.
engineering might would have a choice because you were more interested in mechanical engineering, or you wanted to explore more in the field.
So I think it's a fair statement to say I've never really had choice. Almost every degree I did was sort of the only option I had. So after 12th standard, you write an entrance test and you go for counseling.
Right.
And so I was sat at a computer and saw which places had a degree to offer and a seat. And because I didn't want to do electrical, I wanted to do something like mechanical. There was only one place in Chennai that apparently had an offer of a position. And the same thing was true when I went for my master's. I applied to many places. For various reasons, I only got one offer from Arizona State, so I took the one offer I had. The story repeats. After I finished my master's, I applied to many places for a PhD. I got one offer. I went to my one offer. After my PhD, I applied to many places. I had one offer. So I have no regrets because I had no alternatives. So I had the one offer, I took the offer, and I made the best of it. So
great. So how was your experience while in PhD at Washington?
I loved it. I absolutely loved it. It was difficult at first because I was transitioning from engineering to more mathematics. So University of Washington has two departments: a Department of Mathematics and a Department of Applied Mathematics. And I got admission into the Department of Applied Mathematics, and the coursework is significantly different, but nevertheless, it was challenging for me coming from an engineering background. There were many things I did not know. There were many things I had to learn on my own. There were many things that they assumed I knew, which I did not. But over the course of the 5 years of the PhD, I think it was, I felt like I learned a lot. I felt like I was challenged a lot. I felt like I found what I was truly interested in. And I made some very good friends. So it was a great time. It was a great time.
There, what drew you to partial differential equations? Was it again no choice, or that was a choice?
I think maybe there's a partial choice here. So yeah, no pun intended. So there was. I joined Washington with an idea to work with a particular professor who was also a professor in mechanical engineering. So I thought that made sense. And I actually ended up doing my master's degree with that particular person But over time, I was taking courses from other people, and I took a course from somebody who would eventually be my PhD advisor, and I really liked that course. That course was about what was called nonlinear waves, which was sort of like a second course in partial differential equations, but mostly focused on nonlinear partial differential equations. And I just found that subject fascinating. And so then I approached that particular person and said, I'd like to work with you, and these are the things I'm interested in. Could we work together? The reason it's a partial choice was he said, yeah, we can work together, but we do what I'm interested in.
Oh.
I said, fair enough. I have no problem with that. Yeah.
Got it, sir. What was your experience like as the S. Chawla Research Assistant Professor at the Penn State University?
Yeah, that was also a wonderful experience. It's a 3-year position, and so most postdocs in mathematics in the US are actually lecturers. So you don't get hired usually to do research. You get hired to teach. So the job that pays your salary is actually teaching. And the teaching load can be quite significant. One of the nice things about the S. Chawla position was it came with a very reduced teaching load.
Okay.
So I had to teach 1 course a semester, and sometimes I could teach 2 courses a semester and keep 1 semester free.
Nice.
So it gave me a lot of opportunity to do research. And again, the department had, when I was there were a lot of wonderful people, and there's still a lot of wonderful people there, and made some good friends. Yeah, it was a great experience where I got to pretend to be an independent researcher for 3 years, sort of feel, sort of do the job, work on things I found interesting. Maybe some would say waste time on things I found interesting, but yeah, it was a great experience. And it's a much smaller town than Seattle. That was one of the bigger differences. There was nothing else other than the university, really. Very small college town, lots of undergraduate students everywhere you see. It was a very different experience, but it was very nice and very pleasurable.
So mathematics is a broad field.
Correct.
Of course, you.
That's correct. That's a fair statement. Yeah.
And it's been widely used in physics, engineering, finance,
That's
almost
right.
everywhere.
That's right.
How would you personally organize or classify this field?
How would I classify mathematics?
As in the departments it's been used in.
Oh,
Or
I'm not so sure. See, let me answer it this way. We classify things with a purpose.
yes.
We classify them to understand more about, the subject. So classification should not be an answer. Classification is the method to obtain an answer. So you classify things to answer a question. The classification is not the answer, right? So if I want to split the subject up, I'm not splitting it up because I think the split parts exist. I'm splitting it up because I want to understand how the parts relate to one another, how they relate to other things, what I view is interesting.
Okay.
It's not so much that the split is important. So it's almost like you do it as an exercise, but don't think that the answer is what matters. What matters is the understanding that you get. So with that as a sort of a preamble, mathematics is probably one of the oldest subjects,
Yes.
right, of humanity. And what I find truly interesting is that almost every culture across the planet has a tradition of mathematics, right? Everyone has their own numbering system, their own ways of counting. Everyone has contributed to this huge body, and somehow this body is self-consistent. That the mathematics that some Greek person did, or a Babylonian did, or an Indian did sitting in Kerala, like it all fits together. And so I think the reason why we are interested in applications of mathematics is the reason why we do mathematics. Is it's a human activity. It finds its use in all human activities, and it's one of the oldest activities that we've been doing. So it is everywhere because it's what humans do. it is interesting because it's what humans do. And it is, uniting us because it's what humans do, right? I view mathematics as a subject in the same way that somebody might view architecture. It's the story of cultures, and cultures influencing one another and teaching one another and building new things. And you can use those words to describe mathematics. Cultures learning from one another, teaching one another, building new things.
Right.
And it's one of the things I think that I would say makes us human. What makes us human is our architecture, our culture, our language, our food, our songs, our mathematics. It is an inherently human activity, right? It is what distinguishes us from various other animals, maybe they do some amount of counting, maybe they do some amount of mathematics, right? But we do it in a way that is, I would say, advanced. And I think it's a human activity. So I'm not so interested in the divisions of mathematics. I'm also not interested in promoting a view that all mathematics is beautiful. But I do think all mathematics is used by humans
of course,
for various purposes. Some for artistic purposes, some for financial purposes, some to put a rocket on the moon. But it's used, and I think that's the fun bit.
Okay. So did you ever fear mathematics?
No. So I don't think I ever. I'm lucky. I understand that a lot of people don't like mathematics. I don't think I ever feared mathematics. I don't think I ever felt that because I didn't understand that it wasn't for me. It's also true that I probably did a lot of reading on my own, and I wasn't listening to my teachers. I think that's probably true.
That's going to be a golden line of our podcast. He's not listening to his teachers.
Well, see, I'm not promoting this as a strategy. I'm just telling you what I did. And in all honesty, I don't think I listened to the teacher or waited for the teacher to explain something. I kind of went about it on my own way, and I would read the book ahead of the whole year. Maybe I understood, maybe I didn't. But it was sort of my way of approaching the subject.
Okay.
And I think what happens when you try to do things on your own and you are even teeny bit successful,
right,
you end up developing an intuition.
Okay.
You end up developing your own viewpoint.
You realized that as a school student?
No, not at all. I realized this probably as a postdoc.
Oh.
Like this.
And this mindset that we just discussed about you telling why we should not classify mathematics and how you consider it as
let me be precise. You can classify it, just don't think that the classification is the point.
Just got to say.
Right.
So that mindset, when do you think you realized this thing? Like, this is a cultural thing. You realized it lately in your career, or was it very clear?
I think probably, I think maybe in the last, let's say, 7, 8 years is probably when I consciously came about it. But the idea that, mathematics is as much of a cultural human activity, I think I used to tell that to my students in Penn State. So I had a lot of students from engineering, different branches, who used to hate maths.
Yeah.
And so I used to tell them that, hating maths is like saying you hate art. And you can legitimately hate art. That's a perfectly fine statement to make. But what you are hating is a cultural activity.
Yes.
And I think mathematics stands apart in terms of cultural activities in that it is, some would say, as beautiful as it is useful. Now, there are certain cultural activities that are tremendously beautiful, but not as useful. And then there are other cultural activities that are tremendously useful, but not beautiful. And I think mathematics being sort of embedded in every human activity, there are aspects that are useful, there are aspects that are beautiful, there are aspects that are both, there are aspects that are neither. And I think, that's just mimicking the diversity of human activities. when you are so deeply involved, like let's say language.
Right.
Some languages are beautiful, some languages are not so beautiful. The way in which languages evolve can be interesting. The way in which languages merge can be interesting. And so, if you were to replace I don't like maths with I don't like language, that's a very odd thing to say.
Yeah.
And I used to tell my students, like, I don't want to change your opinion,
Yeah.
but I want you to recognize how odd it is to have that opinion. And if you happen to change, that's on you. Like, I had nothing to do with that.
That's great.
Yeah.
Continuing on the hating mathematics part.
Yeah.
The next question is.
Yeah. So just sort of summarize. I don't think I ever hated mathematics.
About a general opinion. Yeah. So nonlinear partial differential equations are known to be very complex.
Yes.
And could you help us understand why these equations are so difficult to solve?
Okay. I think maybe a good place to actually start is, are things supposed to be easy? Like, is the default position you have on something new that it is easy? And I think most people will acknowledge that if you see something new, or most things in the world are difficult, and that the easy things are actually, the rare, the things that we like, the things that we focus on maybe, but the sort of average thing that you get exposed to, the average concept in economics, the average, word in the English language.
Right.
However you define average, I don't want to get into that, but is the expectation that things are always easy. And I don't think that's true. I think we identify through science, through culture, those things that are easy to communicate. And then we get an idea that most things are easy. But then when you start investigating all things, you kind of realize actually most things are hard. So nonlinear PDEs are hard because they represent the typical PDE. And so the typical PDE is hard because it has no special behavior. A lot of the PDEs that we use in physics and engineering happen to be linear PDEs, but they are precisely used because they are easy.
Okay. Just to get an idea of it.
Just to get it right. So just to understand sort of how the solution looks like, because we can do things, we can find solutions, we can, approximate solutions easier. That's why they get used. So what's interesting is to not ask, are nonlinear PDEs hard? I think what's interesting to ask is, what makes a PDE easy?
Okay, let's go there.
Right? And I think what makes a PDE easy is identifying mathematical properties that allow you to manipulate, that allow you to approximate, that allow you to make substitutions or find answers. So what you really, the more interesting question is to ask is, what makes a problem easy, as opposed to, is a problem hard?
That's a good shift.
When you ask what makes a problem easy, you are actually now doing mathematics, because you're asking, what are the properties that allow me to do this? What are the properties that allow me to do that? What are the properties that allow me to make substitutions? What are the properties that say this problem is equivalent to a much different problem for which I know the answer? That's what you're really trying to answer. Now, when we work with nonlinear PDEs, we don't work with arbitrary equations. We work with those equations we have interest in because of some application or because of some mathematics, that it has some special property. And I think a lot of times these two things tend to go together, that once we've identified the property, we know where to use it, or the fact that somebody is successfully using it hints at the existence of a property. I think my job is usually to sort of talk to several people and sort of point them that, by the way, this is the same thing. So I have a much simpler job. Okay. I don't have to do much. I just have to talk to people and say, you're talking about the same thing.
Great.
Yeah.
PDEs in dynamical systems.
Yeah.
PDEs in dynamical systems often come as a coupled equations.
Right.
So
right.
Why is that, and is there a deeper reason for the coupling?
Yeah. So I think PDEs is probably the broader subject. There are partial differential equations which are not considered dynamical systems. Things like steady state solutions to problems, steady state distribution of temperature or stationary distribution of something, those are typically not dynamical. By dynamical, we mean something that changes with time.
Yes.
Right? So the broad area of PDEs contains both dynamical and non-dynamical equations. I have a preference for dynamical systems, largely because I find them, I just find them personally very fascinating that, you are describing change in time of a system. You get to produce pretty pictures, you get to produce movies, you get to have an imagination that something is happening. Right. And I think, we're surrounded by phenomenon like the weather, the stock market, where things happen in time. A lot of human experiences happen in time. Something happens and then something happens as a result. So there are causal connections that we experience. And so if I'm interested as a applied mathematician in areas of mathematics, areas of PDEs, which have lots of broad application from one area to another, dynamical systems sort of fit in very nicely, and that's sort of why I like to work on both.
So what kind of tools, numerical or analytical, would you use to approach such interesting problems?
So maybe I'll start with the numerical. Computers are, of course, used throughout, and it's a wonderful thing to be able to find solutions or approximations of solutions on a computer. So computer programming is something that is very important. Being able to write code, being able to structure algorithms, all of that stuff is very useful. On the more theoretical side, I think it's actually quite interesting how problems in PDEs have motivated a huge amount of pure mathematics. So the quest to understand solutions to partial differential equations, let's say from the time of Fourier. So when Fourier develops his theory of heat conduction, solves what we now call the heat equation, he uses this technique, which we now call Fourier theory, which is essentially finding solutions to these equations by adding sinusoidal functions, trigonometric functions. So the things in 9th and 10th standard that you absolutely abhor turn out to be extremely useful when you want to solve linear partial differential equations. And Fourier, in I think the late 1800s, comes up with this methodology to find special solutions. And that, interestingly enough, kickstarts a revolution in mathematics, where most of the established mathematicians don't like Fourier's work because it challenges our intuition about what a function is. So Fourier says you can add an infinite number of trigonometric functions and get a discontinuous function like a step function. And he says this is perfectly legitimate because temperature difference could be discontinuous and it evolves into a smooth profile over time. That's what my equations show. What's the problem? Well, about, I believe, 100 years before Fourier's work, the Bernoulli family, Bernoulli brothers and Euler were all aware of everything that Fourier said. But Euler had been working on a different partial differential equation, which was the wave equation. So he had derived that using his Euler-Lagrange equation. So he had found this equation that described how a string clamped at two ends would vibrate. And he found solutions much like Fourier using trigonometric functions. And of course, we teach this to students in classes on PDEs nowadays. And he saw exactly what Fourier saw, which is you could take an infinite number of such functions and end up with something that's discontinuous. And he said, because a string that is discontinuous is a broken string, and a broken string cannot oscillate. The infinite sum of trigonometric functions must be a meaningless concept. So Bernoulli brothers have the orthogonality relationships. They know how to compute what we now call Fourier coefficients, but Euler shuts down this whole conversation. This is my understanding of the history, that Euler understood all of this, but said, because it represents discontinuous functions, it cannot be a real concept. And so this sets mathematics back by about 100 years, till Fourier comes along and says, I want to do a different application. I want to work on heat diffusion. And now discontinuous functions make physical sense, right? So let's summarize in a very biased way. An infinite sum of sinusoidal functions is a concept that is a mathematical concept.
Yes.
Euler rejects it because he says it doesn't make physical sense for his application. And Fourier accepts it because he says it makes physical sense for that application. And so it's interesting to see how an application can bias your view as to what is true, mathematically speaking.
Yeah.
And so if now we understand that discontinuous functions can perfectly be well described by an infinite sum of sinusoidal functions, and there is now theorems that show convergence of these series in various senses of the word, I think it's interesting to think about the role applications plays in the development of pure mathematics. That if you looked at the wrong application, you'd have the wrong view, which is to say, you wouldn't uncover the interesting mathematics of Fourier theory. So one of the things I like to do as an applied mathematician is to actually look at the same mathematics from multiple applications, so that we don't make the mistake that Euler did.
Right.
And we look for the mathematics. And the mathematics stands on its own, but it is useful, and the application might give you the right interpretation you're looking for if you look at the right application. So it then means you should look at lots of applications simultaneously.
Okay.
You should be doing mathematics. You shouldn't be necessarily focused on one application, because maybe then you miss the boat by about 100 years.
Looking at it from a neutral point of view, in a way.
Yeah, so I guess you could say, if I look at it from all points of view, I'm looking at it from a neutral point of view, right? What I'm trying to do is find out what the mathematics is saying.
Right.
And I'm trying to find out what the mathematics is saying by looking at it from every application. Okay. So I think there are different styles of mathematics. Mm-hmm. I think there are some mathematicians who don't want to look at any application and just want to motivate it by pure aesthetic or what they find an internal sort of structure that they find appealing, and they follow that. Let's say those are people who are not influenced by any application. Mm-hmm. It's false, but let's be very hyperbolic and say those are people who are not influenced by any application. And then I think I represent a different viewpoint where I want to be influenced by every application. But our goal is the same, right? I want to find the thing that is in every application. Right. By looking at every application, I'm chipping away the thing that is the application. Right. And I'm trying to find the mathematics. So I feel like, I don't know if you should call one pure and one applied. I don't like the word pure. It has some horrible connotations. But I feel like there are two viewpoints, right? Okay. There's the viewpoint where you are sort of finding it on your own. And then there's the viewpoint where you're trying to somehow subtract away stuff. And whatever you're left with must be mathematics.
Great. You will be bringing divine changes to the mindset of your students. It feels like now I'm interested
I hope
in
so.
mathematics. Now I'm a physics student. I've completed MSc, but now I'm interested in mathematics.
Very good. I've done my job.
Yes, sir.
I've done my job. Yeah.
Talking about applications, would you like to share your experience with applying PDEs to a real world application?
Yeah, I would hesitate to say real world, but there have been a number of applications that I've worked on. I'll start with some of the stuff that I did earlier, which was more along the lines of inverse problems. Okay. An inverse problem is the upside down version of a forward problem. So, great. But that asks, what is a forward problem? A forward problem is the easy problem. The inverse problem is the hard one.
So make an easy thing hard.
Right. But now you might ask, why would you ever do such a thing? I'm going to argue that almost everything that we are interested in is actually a version of an inverse problem. So let's say you are building, I don't know, you're making a table, and you want to make sure that this table is solid. One way you could make sure that it's solid is to cut it up at each point and check whether it's solid. That is a terrible way to check because you've just lost your table. So another thing that material scientists end up doing instead is they tap the material, and then they listen to the sound on the other end. And if there are holes in the material, the tap will sound different, right? So you can, let's say, sometimes in certain movies, somebody's tapping a wall to find a secret door. And how do they do it? Well, because they tap it and then they realize, oh, the sound is different. It's hollow. So somehow we can infer material properties, the density of the material, by listening to sound. So what are we actually doing? What we're actually doing is creating a disturbance in a wave equation that propagates sound. And you are listening to the sound wave, which is to say you are measuring the solution to the wave equation. You're measuring the pressure, because that's what your ears are doing. So you're measuring the pressure of a sound wave, but you're trying to figure out the density of the medium.
Yes. If it is solid or not.
If it is solid or not, or if there's a pocket or not.
Yes.
This is called an inverse problem, because usually when we teach students how to solve partial differential equations, we say, here is the equation, here is the initial condition, let us find the solution. But what I just described is, here is the solution, let us find the equation. Right? But that's the experimental problem. The experimental problem is find the coefficient in the equation that represents the speed of sound. And that is related to the density by various physics, and so maybe you can figure out the density map. This is actually how we discover oil, petroleum.
Okay.
It's the same process, except instead of finding holes in a table, you find pockets of liquid petroleum in the ground, and you do it the same way. You set off an explosive, which is your tap, and then you put a microphone somewhere else, and then you listen to the sound. And you spend a lot of effort understanding how to unpack that information of the medium from the wave. Some physicists work on things, on data coming from CERN. And in CERN, what you do is you throw a particle at another particle, and then you don't actually see the particles. What you see is the sort of emissions of an interaction. And from that, you have to figure out what particles were created. Yet again, you are looking at the solution, and you're trying to figure out what is the potential or what is the particle that was created. Sometimes they call this inverse scattering. So a scattering event is where you send in light and it scatters because of a scatterer. But what I really want to know is, what is the scatterer that caused this scattering? It's the same thing that LIGO is doing. But LIGO is doing scattering with gravitational waves, not with sound waves or electromagnetic waves. But what I am saying is, these are all inverse problems. And these are all experimental science. So a lot of experimental science is a version of an inverse problem, where what we are after are parameters, numbers that define some property. And we rarely get to measure the property. We only get to measure results. And we need theoretical models to connect those two. And so some of the earlier work that I did was a version of an inverse problem, where somebody said, here is a measure of pressure at the bottom of the ocean at a certain location as a time series. What is the height of the ocean? As the wave passes by, the pressure changes.
Yes.
I don't have a way to measure the height of water by putting a stick. What I have is a pressure transducer, typically a piezoelectric crystal. So as the pressure changes, current comes.
Yes.
I can calibrate the current to the pressure. Yes. But what I want to know is the calibration of the pressure to the height. Now, if you assumed that the water was still, you could do what Archimedes did, and you just use rho gh.
Yes.
But the ocean isn't still. So the pressure you measure is not the still water pressure. It is the hydrodynamic pressure, which involves the pressure caused by velocities in the fluid. So now, how do I actually back out that translation? So that was one of the PhD problems that I worked on, which is find a mathematical theory, prove that one can actually find this in the circumstances, given pressure data, find height. There was another problem I worked on, which was given shape of the ocean surface, let's say it's time dependent.
Okay.
So I'm telling you how the shape of a surface evolves. Tell me the shape of the bottom of the ocean. Right? So these are inverse problems.
So what makes inverse problems difficult? Is it that there are multiple
very good question. Very good question.
Solutions to
wonderful question. So inverse problems are what are called ill-posed.
Sorry?
Ill-posed.
Okay.
As opposed to well-posed.
Okay.
Right? And what is ill-posed? Something which is not well-posed.
Yeah.
What is well-posed? A well-posed problem should have a solution.
Right.
So existence.
Should have a solution.
Existence.
Yeah.
A well-posed problem should have a unique solution. So you don't want just a solution, you want a unique solution. And the solution to your problem should change by a small amount if you change your problem by a small amount.
Okay, so you also want that range.
Right? Now, why is that a very useful thing to do? Well, usually you will have an input like some measurement, and you have to extract an output. Because it's a measurement, it has noise. So you'd like your output to only change by the amount of noise. And it shouldn't be so sensitive that if I change my input by a tiny amount, my reconstruction or my evaluation of the property of the medium or the scatterer changes dramatically. Because that forces my experimentalist to work even harder.
Yeah.
And what this really ends up meaning is that you can't trust the results of a reconstruction. By the way, everybody who has taken an MRI, everybody who has taken an X-ray, has effectively done some kind of an inverse problem. Because what you're doing is looking at the scattered event of an X-ray and trying to figure out the medium. And what you don't want is that, there could be a huge change in the shape of a bone, but the picture on the X-ray is the same. That would be an ill-posed thing. That would be terribly ill-posed. So we are interested in those inverse problems or ways to change the problem such that we can make reconstructions that are stable. That's the technical term that we use. They are stable reconstructions. Now, a lot of things as they happen in time can be stable. So let's give you an example of something that's super stable. If I were to take a hot cup of coffee, just leave it there.
Yeah.
Eventually it'll become a cold cup of coffee. So the temperature sort of reaches a certain state. If the conditions of the room don't change and you bring your cup of coffee and I bring my cup of coffee, even if they are different temperatures, they both reach the same temperature. Now, if we were to ask the ulta question, like whose cup of coffee was hotter, that is an unstable question because everybody reaches the same temperature or very close to, even if not exactly the same, but too close.
Yeah.
So now we don't know how to go back. That's an unstable problem. Now, the problem of finding the shape of the bottom of the ocean, given the shape of the surface of the waves, happens to be one of these problems. So one of the works that I had to do was find ways to control that reconstruction error. repose your problem in a certain way, or only say, I can compute things up to a certain accuracy and not any further. Because if you demand further accuracy, then I'll be unstable, right? So I think this is the kind of stuff that I found truly exciting, because it is very applied.
That's great.
People want to know this kind of stuff, but it is also very hard. So that's the kind of problem I
I
like.
think we'll need a second lecture series to understand how you do it, until how do you know about what extent would
For
it
sure.
be accurate.
Yes.
So
Yes. Yes.
moving ahead with in recent years, there has been a trend of using AI and machine learning to solve PDEs.
Correct.
Can you explain how these methods are applied and how reliable they are?
So I think the first thing to say is, this is a subject that's evolving. By the time I finish the sentence, I'm already outdated in my information, so it's hard to sort of keep pace with the changes that are happening. I think the ways in which AI has, and especially neural nets, have been used are fairly significantly different from how we traditionally solve partial differential equations. The allure of these AI methods is that they allow us perhaps to solve equations which depend on many, many, many variables much faster than traditional methods would. Unfortunately, we do not have a good theoretical understanding of AI and neural nets in general, but certainly AI and neural nets applied to PDEs. There's some work that's been done over the last 5 to 10 years, some good work, but I don't think the story is settled that these methods can be used to the same level of reliability that finite element method is used by engineers. I don't think we're necessarily there yet, but like I said, the allure is that they allow us to solve things that are much in higher dimension than we can before. I think most people know me as a bit of a skeptic in this field. I am skeptical of a lot of these results. I think time will tell whether these are actually as good as all the claims are. Some methods are certainly better than other methods, but there's a lot of work to be done, and maybe that's a lot of research has to be done as well.
Got it. You are interested in the intersection between dynamical systems and data
Yeah.
science. Could you explain how this field looks like and how is it evolving?
Yeah, so again, this is one of these fields which seems to be evolving in the last 10, 20 odd years, much more. As I said, a lot of dynamical systems find application in many, many fields.
Yes.
And the interesting thing comes when those application domains come with data sets.
Okay.
And so now you have measurements of dynamical systems which are maybe useful to study the dynamical system, or to solve inverse problems for dynamical systems, or to provide alternative ways of describing solutions to dynamical systems. So I think one of the more interesting things is this intersection between data science and dynamical systems, is that I think it really highlights the importance of inverse problems, because you have measurements.
Right.
You have access to the system in a way that traditionally one does not think of. So we don't just say, here is the initial condition of the system, here is the equation for the system, and this is how it evolves. Now I have measurements all along the evolution path. Maybe I can use that to update my understanding of the rule. Maybe I don't know what the rule is and I can figure out the rule as I keep learning more. So I think there's a lot of interesting questions here. Many of them take forms of inverse problems, but I think more and more you can also pose them as learning questions. Like, can you learn the rule of a dynamical system from the observations?
So, are there any specific applications or collaborations you worked on and you would find interesting or exciting you would like to share here?
I mean, all my collaborations are a bit interesting. How could I choose one? So I guess I find, look, I currently am working with several people on different things, and I think I like the ability of being useful. I mean, that's such a privilege to actually be useful to somebody. So there is a lot of the work that on the dynamical systems, the data science side, where there's interesting questions, like I said, where we're bringing maybe ideas from inverse problems, control theory, to these type of questions. But then on the other hand, there are also problems where I'm more like a consultant.
As you just said, talking to people and like you're doing the same thing.
That's right. That's right. Where somebody just says, "Look, I don't know how to solve this equation," or "I don't know." So you talk to one of my colleagues, Professor Rama Govindarajan, and that was one collaboration that we had, where she just invited me to sit in on a meeting with her and her student, just to listen to what the student was doing, and that sparked a conversation where I said, "Well, I think I know. Sort of, you're stuck at this point. I think I know of a different way to solve this problem." And that led to a series of papers where we found an application of an area of mathematics and PDEs that I was very familiar with. There weren't too many people at ICTS or maybe even broader India who were very familiar with that. So it was a very nice sort of happy accident where I know something that's useful for somebody who has a problem.
Right.
And I was like, well, I think I can help you. I like playing that role from time to time. Sometimes the answer is just, this is well understood. Here's a book. If you have any questions, come ask me. Other times it turns out, oh, this is actually an interesting question. Nobody knows the answer to. Maybe it's something I want to work on.
What are some key skills or habits you try to develop in your students?
That I try to develop in my students?
Yes.
Oh, I think you should ask my students. I think I don't know if I'm successful at this. I don't know if I actively try to do this, but I do hope that everybody is willing to read and sort of push themselves. Like be a little brave. Like it's okay if you don't understand, and it's okay to expose yourself to things you don't understand. The more comfortable you get with that, I think you can have conversations with many, many, many more people. And the more conversations you have is sort of how you learn. And sort of you can make those connections. So, I mean, I would say, really devote some amount of your time to learning something that you have no background in. Read stuff that you don't know too much, or just be curious. Like genuinely curious. Like I feel like if there's one thing I find frustrating is when a student says, "I find this boring." I'm like, I don't think we get to say we're bored of something when we know everything about it. So unless you are an expert at something, you don't get to say you're bored. So if you don't know something, it should be endlessly fascinating. And I feel like if students have that viewpoint, that would be fantastic. I don't know if they have that viewpoint, but that's what. Yeah.
Great. How was your experience at ICTS? Since joining in 2015, what makes it a unique place for doing mathematics?
So it's been great. As I said, I like to do a kind of mathematics where I work on multiple applications simultaneously to find the mathematics. I think ICTS is a fantastic place to do that. If I were in a more traditional mathematics department, I think I would be surrounded by mathematicians. I think I would still enjoy myself. So I don't want to disrespect my hypothetical mathematical colleagues in another universe, but I think if I want to be exposed to different applications, I mean, ICTS is a fantastic place because I think it's almost like a mixture of multiple departments. I mean, you've got people with physics backgrounds, engineering backgrounds, people interested in biology, people interested in atmospheric science. Right? You don't find places in the world where somebody like me can also sit amongst everybody and sort of say, well, actually, you guys are actually doing the same thing. And I think that's a strategy that I've developed more after coming to ICTS, where I actively try to work with a lot of people in different applications. And this whole idea of trying to find mathematics by subtracting away the application over all applications. Again, I think ICTS was probably an ideal place to develop that kind of a viewpoint.
Great. Would you like to comment on the architecture and the culture that has been brought over here? Like, it doesn't feel like India.
It doesn't feel like India?
Yeah.
Oh, I see. Okay. Maybe, I mean, credit probably goes to, everybody who's been, like the senior faculty who've hired all of us. And I think a lot of us bring very diverse opinions, and we've had, our own experiences. Um, it is true that a lot of us have had some foreign experience, so maybe that's why it doesn't feel like India. Uh, but I think it was also an attempt to do something that is just different, not just for India, right? I mean, I think, again, if I look at my colleagues, people I did my PhD with in the US, who may have ended up in traditional mathematics departments, I think even they're envious of, or I like to think so, of the kind of atmosphere and sort of place that ICTS is, right? I mean, it's not just the fact that you have faculty from different areas, you also have programs going on. And so there is an absolutely other avenue to meet people, so who are in completely different areas, right? So programs happen in areas where there's no research in ICTS that happens in those areas. So programs bring in a whole new crowd. So I think maybe the fact that so many people, we have so many visitors, and it's a great place to visit, and it's a great place to meet. It's a great place to have conversations. Maybe that's what makes it so different. But hopefully other places in India do this as well. I don't see why not. I mean, why should there only be one such place? I mean, the more the better.
Great.
Yeah.
How do you see the future of mathematical sciences in India, especially the interdisciplinary research, including biology, mathematics, physics,
Yeah,
everything,
yeah.
finances?
So I think more interdisciplinary stuff is happening in India for sure. At ICTS, at TIFR, there is a program called the Physics of Life, where we try to bring in people who have traditional science, physics, uh, engineering, computer science, mathematics backgrounds into biology to solve problems in biology. So, I mean, I think that's a wonderful example. That's a TIFR program. That's a wonderful example of interdisciplinary science, and it's an active engagement to get people to do interdisciplinary things. I think there are lots of other places in India that are trying to do interdisciplinary things. I think there are multiple data science programs, AI programs, where we're trying to do interdisciplinary things. I think, as I said, I find interdisciplinary multi-application viewpoints the right way to do stuff. So I'm obviously biased to that this is a good trend and should continue. I also do empathize with the viewpoint that you should be able to develop core skills as well. Now I don't know what that means and what is a core skill, but I think it's great to have a core competency that you can say, this is a thing I'm good at, right? And the traditional subjects have well-defined core skills.
Yes.
And I think maybe it's a challenge for a lot of the developing areas, interdisciplinary sciences, to sort of define their core skill. I think it helps you develop an identity. It helps you find a community. And I think all of those things are helpful in the long run. I also think once you develop a community and are in one community, I would encourage you to go to another community. Right? So my bias is always like you should sort of transcend. You should create these barriers and then transcend them.
Okay.
I think there's some learning to be done there.
That's great. Adding a little bit more to it, are there any institutional or cultural changes you believe are necessary to support deeper research in mathematical science?
Yeah, I mean, certainly, I feel like just encouraging curiosity.
Yeah,
Let's say from school,
right.
right? I mean, at every level, I think we need to encourage curiosity and questioning, and I feel like we should encourage questioning and be able to answer the questions, and not just say, well, it's too difficult for you. You'll understand when you grow up, or this is, or let me tell you a version that is practically a lie. I feel like we should acknowledge that curiosity leads to questions which are hard to answer, and maybe even admit to the person asking the question that, hey, maybe I don't know the answer. So I think the first step to finding the answer is to say, I don't know.
Right.
And I think maybe that's a cultural issue as well, that sometimes we're unwilling to say, I don't know. And just because I don't know doesn't mean I can't find out. So I think there are these cultural conversations where some people are unwilling to say, I don't know. Some people are willing to say, once they say, you don't know, well, that must mean nobody knows. That's false. Or it means we can never know. That is also false. So I feel like let's not make these kind of straightforward assumptions that if this, then that. And let's maybe acknowledge a level of not knowing and move to a path of knowing. I don't know if these are cultural things, but I mean, they certainly come to mind that I think these kind of viewpoints, having cultural conversations at the school level, at the college level, in households, yeah, there are things we don't know. That doesn't mean we won't know. And there are things that we don't know and can't explain. That doesn't mean we can't reliably use information to still predict. So for instance, I don't know how the details of an airplane work, but they do work reliably. And somebody knows. And maybe in cases of things like how diseases spread and whatnot, there are things we know and there are things we don't. And just because we don't know something doesn't mean we don't know anything. Right.
Talking about the changes in the school level, can you please tell us about your childhood and your schooling days and memories, if you would like to share?
By the time I finished 12th standard, I think I went to 8 different schools in about 2 different countries. So I've had a diverse experience. I was almost always the new student in class. Every year I was in a different school, almost every year. And so I had a very different upbringing as a result of which. So I think I used to rely a lot on myself for entertainment, for friendship. I mean, this was a time before the internet, so you didn't really have ways to communicate with people that you've left. So I think that's probably where I got into this habit of sort of reading for myself and sort of just being self-reliant, teaching myself. And so I think my school years kind of biased me to being very self-reliant and being able to make new friends, but not necessarily deep friendships, and getting quickly into having a conversation about what's interesting to you. Like very soon as a child, you learn that if you let people talk, they'll talk. You don't have to say much if you let people talk. And then you learn a lot.
That's great.
Yeah.
So outside of mathematics,
Yes.
what do you enjoy doing? Any hobbies or skills?
My life is pretty obsessed with mathematics. I think that's fair to say. I spend a phenomenal amount of time, probably spending all my time. I do enjoy cooking. I do enjoy cooking because I enjoy eating, I guess. And cooking is a way usually that I relax, and I like to think things sort of on the back burner. So it's not an active process of thinking. It's me doing something else, but the thoughts are always happening. So yeah, cooking was that. I used to love playing squash. I don't play squash as much nowadays, but yeah, I think nowadays my sort of main interest. So yeah, I mean, I like a challenge. So sometimes I go out of my way to cook something very difficult just because it's interesting. I don't enjoy eating as much as I enjoy cooking, which is weird. So I'm happy to give away what I cook. It's perfectly fine.
Were there any personal mentors or role models, scientific or otherwise, who had a deep impact on your views on science and maths?
I mean, it goes without saying, my PhD advisor, my postdoc advisor, all of these people deeply influential on the way I thought. My parents, deeply influential. My mother used to take me to the library when I was a kid and would push me to get 5 new books every week. I developed a reading habit because of her. So absolutely crucial. My ability to learn on my own is my ability to read. And the fact that I like reading anything is probably because of this exercise. My father, without a doubt, influencing how I think about a lot of stuff, challenging me. Um, but I guess I should. This is somebody I haven't mentioned in this kind of a forum before. But in 10th standard, I took tuitions for maths. Um, I think my parents were probably nervous about 10th standard board or some such thing. So after I finished 9th standard during the summer holidays, they said, go do maths tuition. So my maths tutor, um, Mr. Parekh in Jaipur, he was probably really crucial to sort of pushing me in my sort of the first time ever to sort of be independent and do mathematics. When I would go to his tuition class, quite often I had already read the book.
Okay.
And so he would allow that and sort of say, well, okay, then why don't you explain what's happening to somebody else? Like, work it out. Like, you explain it, I'll just listen. So I think that was probably the first time that I was teaching, and I think I liked it. And I liked being able to clarify things for myself by teaching. And I think there's one sentence that he's told me that I still remember, which is, he asked me a question. I actually know what question he asked me, but I won't say it. He asked me a question, I answered, and he said, बेटा तुमने दिमाग तो लगाया लेकिन आधी दिमाग लगाया, पूरी दिमाग लगा के बताओ. And it was true. I immediately gave an answer sort of thinking in a certain rote way.
Okay.
And that was the first time somebody caught me in sort of giving a rote answer. And he's like, no, soch ke, puri dimag laga ke, tell me the answer. And to this day, I can hear those words. And it's something that I try to live up to.
That's great. If you weren't a mathematician, would you have been a chef or something else?
If I wasn't a mathematician, would I have been a chef? Probably not, no. I mean, there's a good chance I would have been a doctor like my father. But I'm not good with my hands, so it's probably a bad idea. He was a surgeon. I think, I know, at one point I toyed with the idea of law, I guess. I think there's a lot of similarity between reading, like, the law and reading a theorem. Like, the wordage is important. Right? The ability to argue and find logical mistakes. Right? I think I may have enjoyed that. But it's hard to say. I mean, I tried not to do mathematics by doing engineering, and I found myself back again. So maybe that's proof that I had to end up here.
That's a great answer. Yeah. Looking ahead, what areas of mathematics or science do you think young researchers should be most excited about?
What areas of mathematics and science? I mean, in mathematics, I feel like you could be interested in just about anything. It's not about the area. It's about how you think. Once you understand that what mathematics is really doing for you is shaping how you think, okay, then you are prepared for whatever area is interesting 20 years from now. Right? I mean, I could not have told you learn data science 20 years ago, learn AI 20 years ago. I could not have told you that. But I guess the fact that there's a certain training that involves linear algebra, and I like that subject and I'm good at that subject, means this stuff is easier to pick up. And so I think as far as mathematics goes, learn everything. Learn anything, everything, doesn't matter. Learn what you like. Learn what you don't like. It really doesn't matter. It will change how you think. Okay. And once you have that mathematical way of thinking, which is insisting on definitions, being very clear, being very precise, knowing where you made an assumption, being able to fill in logical gaps or recognize where a jump was made and trying to find justifications for that, that can be learned in just about any subject of mathematics. I mean, that is the point of mathematics. That's also a useful skill in most sciences.
Finally, what message would you like to share with students and early career researchers who may be considering mathematics as a career?
I think there's a lot of interesting and difficult problems related to reliability of AI systems. that probably require some interesting mathematics, statistics. I mean, it's going to be a combination of mathematics, statistics, computer science, being able to develop AI systems that are reliable, interpretable, easy to train. I mean, so far, a lot of the large language models that we have are very expensive to train. That means only a handful or less than a handful of individuals get to train them. More people get to use them. That's great. But maybe we want to develop tools that are also as equitable on the training side. And maybe that requires new ways of thinking about mathematics, new ways of thinking about AI, new ways of doing the training, which is more equitable, more distributive, where no matter, maybe I have trained on a small amount of data and I have learned something, and you have learned something, there should be ways mathematically that we can build and connect these things. And I think these things require new mathematical ideas. So I feel like being able to produce reliable AI systems is an obvious question. Being able to produce mathematics that helps with predicting risk in the climate. I think that's an absolutely essential thing that we have to do. So talking about risk of actions or inactions, how to quantify a risk, how to sort of account risk into dynamical systems so that predictions are made cognizant of risk. I think all of this stuff requires, again, new mathematics. So if you're interested in impacts of climate science, climate change, there's some really hard stuff to be done there as well.
It was wonderful, sir.
Thank you so much.
To conclude this episode right now, but I hope we get one more episode on inverse problems. That was wonderful.
Thank you so much.
That was great. Thank you.
I hope I